good introduction. I'm so glad to be here with you. I intend to give you a perspective from the electronic engineering. My background is electronic engineering, okay? So I will give a flavor about what kind of problems we have to solve, mainly in plant phenotyping, okay? So, and I intend to talk about low-cost and disposable sensors and potential applications for plant phenotyping. I have the, how I can put the laser pointer?
It's a laser pointer.
No?
No, sorry.
Aha. Okay. So I'm from Embrapa, sorry? Okay, I'm from Embrapa Instrumentation, and the Embrapa Instrumentation, we are from Brazil, in São Carlos. Okay, at the Embrapa Instrumentation, we have the National Lab in Nanotechnology, applying agriculture, and the other facility is about National Lab in Precision Agriculture. Okay, and over here is a map where we are in São Paulo state. Basically, our team, we are in 31 researchers, and 9 physicists, 7 electronic engineerings, 4 materials engineers, chemical, agronomist engineers. So it's a multidisciplinary team, basically to apply instrumentation in agriculture, okay? And we have more than almost 300 students, undergraduate, master's, doctorate, and postdoctorate students working with us. So the main motivation, what's the main motivation here? Is the fully printed sensors will reach 7.6 billion revenue by 2027. The plant phenotyping market is a growth, okay? And the ultimate success of the chemical biosensors and sensors resides in design and expensive, single-use and reusable, reliable, and sensitivity. And one exciting challenge of the first part of this century is the development of ship, throwaway, electronic device using electronic circuitry deposited on plastic, fabric, and paper substrates. So this is our motivation as electronic engineering and the instrumentation, and to apply in plant phenotyping. Basically, when you look at the sensors, we have 17 features, 17 characteristics that you have to look. Static, accuracy, distortion, hysteresis. So all of this is very important that you have to consider to do a good sensors. But basically, we have to look at accuracy, sensitivity, and repeatability. If you have all of these 3, okay, we have a sensors. Okay? And the definition. One definition that I found that is a very good. The low-cost sensors technology is defined as a sensor technology originally developed for consumer applications and or research. Competitive and low cost because of the economy scale. Okay? This is one point. Okay? And this sensors technology enable new applications or allow more cost-effective utilization of the sensing in production and environments. So, consumer application and research. For example, thermometer to fever is a sensor, okay? It's low cost sensors, but this is important sensors. It's an indication. This is the key point, indication. And the is important part in the sensor is this transducer. What is transducer? We have some physical, chemical, biophysical, biochemical energy and you have one system, that the transducer, to another form of energy. And this transducer, basically, we have an input, the sense elements, and the translation in the element, and the output. So basically, we have to look at this. Okay? How long I have? Just 10 minutes, yeah? Okay. This is the total. The sensor is the transducer and the electronic system and the data processing. So we have a transducer that you have to look, okay? This is a research that you have to do. And when you have the electronic system and the data processing, we have a sensor. In this case, we are discussing about transducer and how to evaluate the signal from transducer. And in this case, you have electronics and you need data processing. Basically, in the low cost and disposable sensor, we are using a technique called line patterning technique. Basically, we have to draw our electrode. Okay, we have 3 steps in the transducer, basically. The substrates, the electrode, and the active layer. Okay? And in these disposable sensors, and we are discussing the technique to develop this line patterning technique. We need to draw the electrode, you need to do inversion, you need to print this in the paper, or in the plastic, or in the cloth, and we need to do a deposition of the active layer that we are using polyaniline. This is a conductive polymer, okay? And the last point is the removal of the printing. So we are using this technique to develop these disposable sensors. This one, we have the graphite, the lining patterning of graphite in transparency, paper and cloth. Okay, this is shown. This one is now you have one transducer, and this transducer is connected with the electronic system, and we have one sensors to detect gas. Okay, this is a gas. And we can develop in the sensors, the double phase sensors. This is what we have. So I would like to present here, but anyway, we have the confirmation of the response of the sensors with air and water, and vapor water. This one is the banana ripeness. We are using this in the banana ripeness. This, as I said, this is low cost. We don't have a high amount of sensitivity, and you have the lining pattern, the synthesis. We have the chamber, the gas chamber, and inside of these gas chambers, the sensors, and the electronic system that we developed to do this. The other part is the results, that the response. We have the banana inside of the chamber and the outside of the chamber, and how was all of these sensors responses, the different sensors, is the different active layers, okay? Each active layer has a different response, and we can see and we can evaluate the response. And in electronic nodes, we have an array of the sensors. Now the next step is the data processing, the principal component analysis, and we can show that each sensor has a different response, and show to us that you can use the system like this in the banana ripeness. This one is the key point. I show to you the sensibility, and this one showed to us the repeatability and sensitivity. So we have sensors, okay? The other point is a new example. It's about plastic pH sensors. This one you have the same procedures, the lining patterning and the polyaniline in situ deposition. This one showed to us how to change the colors, okay, with the pH. Basically, we have the same principle, the Lambert-Beer attenuation, and we are measuring the correlation between the attenuation and the pH. These are low-cost sensors, okay? We have the resolution here and the equation, and you have repeatability and reproducibility. So we have the sensors. And this one is to show, for example, as I said, before to use expensive sensors to conduct some research, like in this case was in the lake, why not to develop low-cost sensors and affordable sensors to find a good place to do measurements and to put in the boat a very expensive sensors and to do accuracy measurements over there. This is the basic principle that I show here, and to show the measurements of our pH and the expensive sensors. Very good correlation. So this shows to us that you can measure in the depth all of these measurements. The other point, just to finish here, is about affordable optical sensors, that in plant phenotyping, basically we are using optical sensors. So when you compare the past, in 1975, you have a Kodak. This was the first affordable optical sensors. This had 10 kilopixels, okay? And in present, we have these RGB cameras, is around 40.1 megapixels, and the 3D cameras and the smartphones, yeah? And in the future, that we are discussing this, about the future, how to apply these affordable sensors. The graph here showed to us how to improve the numbers of the pixels during the year, during 43 years, and the price decreased a lot of. So, and today the numbers of the smartphone is around 2.5 billion smartphones, yeah? And in the future, look, this is not advertised, but is a smartphone with a 3D camera. We have the 3D camera in the smartphone. So, and about sensors, the optical sensors, the future, past and present, you have, as I told you before, this is in the electronic view perspective. We have the CCD and the CMOS sensors, okay, in the past, in the present, wireless connectivity, high megapixel counts, enhancing image quality with increase of megapixels and filters. And in the future, about sensors to optical sensors. Organic sensors can switch between visible and near sensitivity. You can have the same information, both information in just one sensors, okay? Increase the numbers of the megapixels on the same size sensor. This is very important in the viewpoint of the optical methods. Enhance the image quality, but not increase the megapixel. Enhance the image quality, but not increasing the megapixel. Because normally you are expecting that when we have increasing megapixel, we have a much better image. But it's not in this way. And the reading of all pixels in parallel. This is important to time. And some proposal to plant phenotyping. Low-cost gas sensors to detect the biotic and the abiotic stress, as I showed before with this system here. The piezoelectric microphone applied to photothermal system to conduct investigation of the thermal stress. Smartphone and the apps to measure the intensity of the lights, for example, as showed before here in the first seminars, the numbers of the applications, and the smartphone adapted to the spectrometer. And some acknowledgments to my two students, our CNPQ, National Science Foundation, Embrapa LabX Europe, and Embrapa with other projects. And thank you very much.